media, high-speed networks, and cryptography. You ready?
Ready. Good afternoon, everyone. My topic is general frame level segmentation for periodic broadcast of VER videos. And this is issue in video on demand. So agenda here is first we will talk about some facts. The next is the two problems we found in the current VOD broadcast schemes. And next, we will provide our solutions. Then we give out the conclusion, the reference, and the last way, the question and answer. First is the fact is that video is a sequence of frames, and to improve compression rate, some frames use backwards prediction. That is requires future reference frames. For example, the B frames in MPEG. For the sequence of frames that's using the backwards prediction, the display order is not equal to the transmission order. The display order, a sequence of frames in display order is a sequence of frames that this sequence of frames is output of decoder. And the sequence of frames in transmission order is the input of decoders. So here gives a simple example. For example, this is a sequence of frames in display order. Here I, B, and P are types of frames. And for P frames, it only use the forward prediction to improve the compression rate. And for B frames, it use bidirectional prediction. The red one stands for the backward prediction. And the sequence of frames in transmission order of this example is like this, and you will see that these two orders are not the same. Here you will see that for each frame, for each reference frame, it should be in front of each frame that refers to it. For example, the second frame in the display order, that is a B frame, it will use information on the fourth frame and the first frame. So it should be after the first frame and the fourth frame. And here we will focus on the transmission order because the frames transmitted in the network is in transmission order. So current schemes for video on demand, current schemes for videos using backward prediction, there are two problems. One is that the improper decoding. Here is a sequence of frames in display order, and we will see that the second E frame uses backward prediction. And here gives out a simple example is that, for example, here this is the boundary of the segment. So that, for example, in this simple example, frame 1, 2, 3 is in the first segment. And so here, the problem is that how to decode the second and the third frame. There is a problem. So currently, many VOD broadcast schemes only consider the sequence of frames in display order. So here, from this simple example, we can see that transmission order should be used for segmentation to ensure proper decoding. 1, 2, 3. The first, second, and third frames, they are in the first segment. If we want to decode the second and the third frame, there is not enough information for us to decode the second and the third frame because we need the fourth. We need the information of the fourth frame. Other than the first problem, we also find that even we use the transmission order, there is still a problem in the partial display problem. This is the sequence of frames in transmission order. Here we can see that the third frame, D frame, should use the information of the fourth frame, that is P frame here. And we use transmission order to segment the video. So what's the problem here? So after we decode the information we get from the network, that is transmission order, we want to display it, right? And consider the first frame, it is I frame, so it contains the information by itself, so we do not need the information of other frames, so we can display it correctly. For the second frame, for us to decode it correctly, we only need the information of the first frame, fourth frame, and the information contained by itself, so we can display the second frame correctly. But for us to display the third frame, that B frame, we cannot display it because in the first segment we received only contains frames 1, 4, and 2. To properly decode the third frame, we need information. We need the information of the third frame itself also, right? But we currently, at this time, we haven't received the third frame, so we cannot display it. So this is the problem of the partial display. And here is our solution. To ensure both proper decoding and full display, we provide a segment and flag sequence, that is SEF. SEF is, what is SEF? Something that it has the same length of the frame sequence. showing whether a frame can be at the end of a segment or not. So it is a sequence of 0, 1, 0, 1. And we also use the dynamic programming in LLDE. LLDE is a video on demand broadcast scheme, stands for lossless and bandwidth efficient broadcasting. This was proposed by, I think, in 2000. The dynamic programming approach proposed in LLDE, it can achieve minimal server bandwidth given wait time and number of segments. So there is a video for broadcast scheme to achieve the minimal server bandwidth. We can use this scheme. And with this tool, we can get our general frame level segmentation, that's GFLS. So first, how to construct the sequence, SEF. There are two ways to construct. One way is from the display order of the sequence. So for frames that do not use backward prediction, the item in the sequence is the one that frames not using backward prediction can be at the end of segments. So at that position, the item in the sequence is 1. So this is the algorithm. The capital A stands for the total number of frames in the video. If the prediction type, here the prediction type display means that the is array stands for whether it uses backward prediction or not. So if it use backward prediction, so it cannot be at the end of the segment, so it is false. If it is not use backward prediction, so it can be at the end of the segment. Another way is from transmission order. So frames just before reference frames can be at the end of segments. So that this is the algorithm. Is that if the frame do not use backward prediction, not use backward prediction. So the frame before it can be at the end of the sequence, can be at the end of segments. We find that we can get the same SEF from either way. Here gives a simple example using the same sequence of frames as before. So this is a sequence of frames in display order. So according to the algorithm, the SEF sequence is this first frame is I. It do not use backward prediction, so it can be at the end of segment. Similarly, so we can get other ones. It is very simple that all the B frames, that is 0, cannot be at the end of segments. So let's see the transmission order. First, according to the algorithm we described before, for frames that just before a reference frame, it is 1. So here, the first one is Y, because the second P frame is a reference frame. It does not use backward prediction. So the first frame just before the first frame, so it should be 1. Similarly, the frame 3 is before frame 7. Frame 7 is a reference frame. It does not use backward prediction. So the frame 3, the position of the frame 3 is 1. And similarly, we can get all the 1s. And you can see that the SEF sequence is the same. Okay. Also, we prove that the same SEF holds for any GOP. A GOP stands for the group of picture. So the idea is very simple, is that SEF from transmission order, we prove is that it's same as the SEF from display order. The way we use that is one by one backwards. Okay. First, the last item N. N is stands for the number of frames in one video. Is 1 for both orders. It is obvious, right? Because the last frame in one video, of course, can be at the end of segment. And secondly, that for let's assume that K is the first one item in the SEF before last item for display order. And we prove this is true for transmission order. So here is the display order. This is the last item. So it is 1. And we assume that K is the first one item before N. So between them are all 0. And we consider the transmission order. And last one is also 1. It's the same. And according to the transmission order, all the frames that referred to a reference frame should be behind of the reference frame. So the frame K plus 1 to A minus 1 should behind the frame A. And according to the construction rule of from transmission order, this item should be 1, because according to the transmission order rule, according to the construction rule in transmission order, the frame that just before the frame not using backward prediction is 1. So here it is 1. You can see that it is exactly the same. And all the others between are all zeros. So similarly backwards, we finish the proof. Okay, the other main component of our solution is dynamic programming in LLBE. The idea is in the another paper that I will show in the reference. The idea is to construct an capital N multiply small n table B mean for given W. So here, the N is the number of frames in one video, and the small n refers to the number of segments you want to segment the video, and the W stands for the user waiting time. The B mean JI stands for minimal server bandwidth to transmit first J frames in the video using I channels. And W is the user wait time, and capital J is the cumulative size in bits. So A1 is the size of the first frame in bits, and A capital N is the size of the whole video. So this is a table. The first column 1 to J until capital N stands for the number of frames. First step is to initialize the B mean Ji for J greater or equal to I, and B mean J1. So first, here the table. The first column is initialized to the A J over W. So it's easy to understand is that the minimal server bandwidth of to transmit the first frames using one channel is very simple. It's AJ over W. And for others, we just initialize to be the infinity. And for I from 2 to N, J from I to capital N, try K from I minus 1 to J minus 1 to find the best cutting point between I minus 1 and J minus 1 to get the B mean Ji. So the step is that first we find the number of segments is 2. We find the minimum server bandwidth when we transmit the first 2 frames, 3 frames until the capital N frames. After this step, then next step is to compute the minimal server bandwidth to transmit the first 3 frames using 3 channels, 4 frames using 3 channels, then using this way. The detail is in the paper, so here just give the very simple demonstration.